Good evening, ladies and gentlemen, and welcome to the 10th lecture in the Jabrah Reinforcement Learning Series. So in the last lecture, we looked at Monte Carlo prediction, where we say that we are given a policy and we're trying to evaluate it using the Monte Carlo methodology from simulated experience. So we generate a bunch of episodes from a policy, and using those episodes, we are actually going to compute the average sample returns for different states, and basically this is what would end up using for making decisions later on, because we should probably have some kind of model as well. But in this lecture, we are gonna be focusing more on Monte Carlo control. So we looked briefly at the prediction problem, and the idea behind it was clearly illustrated by the pseudocode algorithm that we saw last time. Now we're gonna go to the control case, but before we actually start on that, in order to actually better understand what control is, so we're looking at, oh sorry, I should check. So Monte Carlo control, right? So before we actually look at some of these things, we first need to look at the estimation, Monte Carlo estimation for action values, right? So actually, yeah, before this, let's first look at estimation for action values. So as you remember, last time we were actually focusing on estimating the values of each state, but if instead we were actually given some policy pi and we are trying to estimate q pi of s comma a, right, which is what we're calling our action values, the thing is that we are going to actually arise to a couple of problems, some of which we covered through in the last lecture, like we just hinted towards them. So the thing here is that the reason why we might actually want to estimate these Q values directly is so that we actually have a model-free algorithm that we can actually make use of here, right? So if you want our algorithm to be model-free, if we have the Q values, we can use those Q values, like take the maximum of some sort, if you remember, and using that we can make decisions about where we're supposed to move. But in the other case where we were given a policy and we're trying to estimate like v pi of s, right? So in order for this to actually work, we need a model, right? For this scenario, we need to actually generate our own model based on the sampled experiences and such. So the idea here is that what we have here is a situation whereby we're estimating Q values for state action pairs, but we have a fundamental problem where some state action pairs might not be visited, right? So this is a problem that we might actually face, like when we're doing this kind of simulation. So unless we have some kind of clever strategy for how we either initialize or how we navigate our environment, we might actually have some uninitialized state action pairs. And if you think about it, the whole point here is we're trying to look at a state, look at all the actions that are available in the state, and based on those actions, we're trying to make the best action. But if some of those state action pairs are not even visited, then it becomes more difficult to actually make the best decisions in such scenarios, right? So how do we actually handle such cases? This is kind of like one thing we might have to look at, right? So for that, there are actually, like we hinted in the last video, multiple strategies we might actually use to, you know, kind of like overcome this barrier in a sense, right? So we are going to make two assumptions here. One assumption is going to be called exploring starts. Exploring starts. And the other assumption is an infinite number of episodes. Infinite number of episodes. So right now you might be wondering what these things are. Why are we making these assumptions? I'm actually going to get to that in a second. But in order to do that, it will become more clear when we're looking at the actual algorithm where we're using exploring starts. But to give you an idea, exploring starts here is just saying that when we initialize, right, we should initialize, when we're initializing like our episodes using Monte Carlo, we should do it in a way that every state action pair is actually chosen. So every time we initialize with some kind of equal probability that we start from a random state action pair, right? So of course, if we start from, let's say, okay, random state action pair, right? So as we actually approach infinity episodes, every state action pair will actually be visited. That's the idea, right? So every state action pair will be visited as we approach infinity episodes. That's why we have this kind of assumptions, like with exploring starts and an infinite number of episodes, right? So having said that, let's start with the main topic, actually, of this video, which is Monte Carlo control. Right. So for this video, we're not going to go into the more difficult aspects of this control. Like there are actually a lot of complicated aspects we might face with this. But we're going to look at them in future videos. We're not going to ignore them, of course, because that's not what we do here. So the idea is that, like, with Monte Carlo control, we are essentially solving the same problem that we had when we were doing policy improvement, right? So given a pi s policy, what we're going to do is take the argmax, like to actually compute the policy, argmax over all actions of q s comma a, right? So if you remember this, this is how we were doing policy improvement. And the other thing is, if you remember from the policy improvement theorem, we were saying that if we have q pi k s comma, if we take pi k plus 1, sorry, let me write that better, pi k plus 1, right, of s, which is essentially equal to q pi k s comma the argmax, right, over all actions of the argmax over all actions of q pi k s comma a, right? If we take the argmax over all actions of q pi s comma a, that's how we get this. So according to the policy improvement theorem, this is actually should be greater than or equal to v pi. So this should be greater than or equal to v pi k s, right? So this is accordingly to the policy improvement theorem. And if you remember, we actually went through a mini proof of why this is the case. So if you want to check that out, please look at the previous lectures focusing on policy improvement. So this is what we have. So the way we're actually doing control specifically in this case whereby we're just trying to do something like Monte Carlo control with exploring stars, this is how we do the improvement. This is gonna get a bit more complicated later on, but for now you can take it as is. So given this, what we're gonna try to do is go through the pseudocode for the Monte Carlo control, right? So we do Monte Carlo ES, where ES means exploring starts. So exploring starts, if you remember, we are assigning random probability to each state action pair so that we can start from any one of them, right? So we start with a Q S comma A, which we already said this is just arbitrary, right? And we have some initial pi s, again this is arbitrary, we don't choose this. And then we have this is kind of like the initialization. Okay, so we have this, and we have return of s comma a, right, which in the beginning is gonna just be empty anyway because we don't have returns. So what is the first thing that we need to do? So we're going to repeat the following, right? This is what we're gonna build. So we're gonna choose S0, right, is an element, it's an element of S, and we're gonna choose A0, right, is an element of all the actions that are available in state S0, right, such that the probability of taking A given S0 is greater than 0 for all A is an element of capital A, right? So what this is saying essentially is that we want to make sure that every action has some probability of being taken in the beginning. So this is actually the assumption of exploring starts here. This is what we're doing here, like exploring starts. That's what we're doing, right? So after this, we're gonna do this very same thing that we're doing when we're doing like Monte Carlo prediction. So G, what is G? We compute G as the occurrence, or not say occurrence, maybe just call it the return, right? I'm gonna call it the return following the first occurrence of S comma A, right? So after the first occurrence of S comma A, we get some return from starting from that point. That's what we call G, right? So we're gonna append G to returns S comma A, naturally, that's something we need to do. And to actually compute QS comma A, right, we need to take an average, just like we did in the prediction state, the average of the returns. S comma A. That's how we find our QS comma A. So that's Monte Carlo with the exploring starts assumption. Now we need to do the control part, because all of this is essentially doing prediction but for action values. That's what we've done so far. Now to do the control part for each state, right, in the episode, what should we do? For each state in the episode, pi s, right, you already know what this is, the argmax over all actions of Q S comma A, That's what this bias essentially is. So this actually covers the algorithm for Monte Carlo with exploring stars. In the next video, we're going to look at more techniques that we can use for solving for the Monte Carlo control problem and trying to actually avoid these assumptions of having infinite episodes as well as the exploring stars assumption, because in reality this is actually a difficult assumption to make at times, and there are better initialization methods or like ongoing methods that we can actually use. So see you in the next video. Thank you kindly.